Now look, most engineers who look at a BMS or control system for the first time think, what the hell is going on here? Like, this looks like some kind of black magic that only certain contractors understand. And the truth is, many of them like to keep it that way. Fucking knowledge hoarders. Apologies. They don't want to explain how this stuff actually works, how dampers move, how actuators respond, and what really happens inside those control panels. So in this video, I'm going to break it down step by step and make it simple. You'll see exactly how HVAC dampers and Belimo actuators are wired and controlled using real schematics, relays and control circuits from a live project. And you can grab a copy of all the resources that we're discussing in this training to follow along with yourself from clicking the link in the description. So let's jump in. Certainly like in industrial and BMS, like there's lots of there's ventilation ducts where we use sort of dampers to control the flow of air. So like extraction, ventilation, air conditioning, whatnot. So we're going to look at like the control of dampers. That's the first thing. And then we're going to look at the control of similar sort of thing, actuator valves. So actually so we're not, sorry, I was going to say we're going to look at valves on a hydraulic system, but it's an actuator valve for a ventilation system still. So yeah, you'll see two different types of actuators, but they're both for ventilation systems. So let's jump in and have a look at that. So firstly, just let's paint a picture of what we're actually looking at. So on this first part, we're going to look at a vertical damper. So we got like a vertical damper like this, and then we've also got a sort of a rotary vent damper. So what that looks like, just so you can picture it in your head. So that's the first damper we're looking at, and this is pretty straightforward. It's just we control this damper up, and then we can control that damper down. That's it for that one. So that's the first thing we look at. And then the second one that we look at is ultimately doing the same thing, but we're controlling like the tilt of those vents. So rather it just being up and down, linear motion, this is actually a rotation, that changes the pitch of those slats. So that's the second thing that we'll look at. So this is the schematic. Can you see this schematic, guys? Cool. So in terms of the control and the wiring, because that's what we're looking at, like how to control those dampers and what does the wiring look like of those dampers. So I'm going to show you what it looks like in terms of like an electrical schematic for this vertical damper, and then on the rotary damper, we're going to look at the tech manual. So you're going to get like two bits of it, looking at it from two different sides. They're going to be slightly different, but you're going to get to see it from both sides. This is quite a basic project, so I'll just quickly run through this, like the schematics of this now. So what we've got is we've got our supply coming in here to the panel via this door isolator, and then we've got one MCB, and I'll tell you what, let's try and zoom in a little bit. There we go. So we've got one MCB, which then feeds that power supply. And if you want to see what this visually looks like, then just go to that training within Squad, and you'll be able to see what I'm talking about. So we're going into a power supply. This is the primary side, so 230 volts feeding that, and then on the secondary side we've got our 24 volt DC coming out, and we've got our 0 volts and our 0 volt line here, so pretty basic, pretty standard. And then we've got our 24 volts coming out of this terminal here, going via a fuse. So we're fusing the DC side of it as well. And then we just got a white power lamp that switches on when this power supply is healthy. That's just a visual representation on the front of the panel, so we know that, you know, we've got that power supply is working basically.
Just a quick one. If you'd like to grab a copy of those resources that we're using in this training, you can grab a copy from clicking the link in the description.
Then what we've got, so now we're getting into the controls of it, and I'm just going to ignore this bit here. I'm not even going to talk about this bit here. It's kind of distracting away from the actual control of this damper, so I'm not going to worry about that. But what we've got tapping off this 24 volts is we got a supply, or 24 volt supply, and it's going into the selector switch on the front of this panel. And this is just a 2-position selector switch. Like it's either like not energized or it is energized. So you can see, like, in its A position, it's open, and in its B position, like if we then switch that switch that switch to the B side, that then closes that. Whoops. And it allows that 24 volts to go through here and ultimately energize this relay 1, RL1. And then, as you can see over here, it's a double pole, double throw relay. And as you can see here, RL1. So we got the coil side over here, which is now energized because we switched it to B, which then what happens here, it just basically changes the state of these contactors. And it would be better actually if I had this in my iPad so I could actually draw what's happening. So you have to forgive me, I haven't done that on this, but I can run through it another time if you wanted to. But yeah, basically that is that when that relay energizes or de-energizes, either that contact is in this position when it's selected in A, or it's goes over to this position when it's selected in B. And exactly the same thing happens on this side. So that's just the operation of the relay, but let's just go back a step and just go upstream and see what's happening here. So what we've got, again, we've got 24 volts coming out of the power supply up here, and then it's just going through. What we've got here is just an overload. So basically like an MCB, but it's a thermal overload, specifically designed to protect these dampers here. What we're doing is that if everything's healthy and these haven't tripped out, then that will be closed. So we got 24 volts going down here, and it's being distributed across here into 14 of relay 1 and 22 of relay 1, and because it's a double pole relay. So in this position, just in its normal position, A, when RL1 is not energized, so it's not energized, it's just in its normal state, providing these haven't tripped, we've got 24 volts going through here, and then because these are in their normal state, their normal position, then we've got 24 volts going through here, and then down here, and then to these terminal blocks here. But on this other side of the relay, you can see that it just stops at 14 because this contact isn't switched over this side because it's just in its normal state. So basically we've got 24 volts going down one side, but it's not going down the other side. So what happens in terms of the power is, let's just follow it from the top again. So providing this isn't tripped out, we've got 24 volts going down here, and then we've got 2 dampers. So this system, I'm complicating it a little bit, but this is just the way this system was, or this system was. We basically got 2 dampers where one damper is completely open and the other one is completely closed. And what we're doing through changing that selector switch is we're just changing it like that. So then it inverts it. It goes around the other way. So I am adding a little bit of complication into this in terms of explaining how this is controlled and wired. But yeah, that's kind of the project. So 24 volts going down here, and then it's being distributed across terminal block 3 and 4. And these are the polarity of these dampers. So A is a damper and B is a damper, because that correlates then to this switch here. So we kind of got A damper open, B closed, or we've got B damper open and A closed. So as it is at the moment, whoops, we've got 24 volts coming down here via those terminal blocks, and then we're powering up the negative side on A, and we're powering up the positive side on B, and the polarity doesn't matter. So we're doing exactly that. We're powering one down, and we're powering one up, and we're powering one down. And then let's say we then switch that switch to now the other way to B. Now we're energizing this relay, which then switches the state. So now let's imagine, because it's energized, that this contact here switches over to 14. It stays in this common. 11 and 21 are the common. So it switches, it stays here, but it switches over to 14 from 12. And the same thing, 22 to 24. And now what happens if we follow it from the top, providing they haven't tripped out? If we go 24 volts down here, now we can't go any further here because the relay's energized. It's the contact switched over here now. So we're not going any further here, but the contact over here is switched to 14. So we're now sending the 24 volts down this route onto these terminal blocks. And then we're just reversing what we had over here on this side through just changing that switch. So if we had, say, on the foot, when it was selected on A, we had A open and B down. Now we switched it over on the selector switch. We've now got B open and A down, if that makes sense. So that's kind of the control of those vertical dampers. Let me just pull up the image again. Whoops. So yeah, that's what we're looking at here. We've got like two of these, and literally we're just sending power until it goes all the way to the top. And then there's like, we're still applying power. We're not cutting power, but it kind of just stops at the top or it stops at the bottom. So we kind of just we've got no module, there's no real control. It's just there's no modulation. It's just kind of opened or closed. It's almost like a digital signal. There's nothing in the middle. It's either fully open or it's fully closed. And on this project, we're just switching it from, A open, B closed, B open, A closed. So that's kind of the control and the wiring on these vertical linear dampers. Before we move on to the next one, which will be a little bit easier to understand in terms of the physical wiring, because we look at the tech manual, does anyone have any sort of questions on looking at it from a schematic control perspective? And have I made it? Is there anything that I've missed or that you don't understand?
Hello, Chris.
How's it going, mate?
Hello there. How are you? Congratulations, by the way.
Oh, thank you. Yeah, it's pretty full on.
It is indeed. Just the only thing that, to be fair, having gone through the course, from a controls perspective, that looks relatively straightforward. What I'm not quite getting, though, is why we're going through, maybe I missed it right at the start, but why are we going through the malarkey of powering the positive and negative on one side and a positive negative on the other. What is the purpose of that? Would it not be the case that you have perhaps a supply to power the unit up, to power the damper up, or to open it, and then one to close it? I'm not quite getting why we've got these different polarities and whatnot.
Because this is just because the nature of this project, it's just come down to like the specification of the project, and what we actually needed to do in terms of the controls determines why it's been designed like this. But I just wanted to give you kind of a real world example of how we would be using like a damper. How would we control it? Just the nature of this project was the spec was basically, without going into all the details, is we've got 2 dampers on a ventilation system. When we want to be able to just through a switch on the front of the panel that you can see here, A/B, we just want to, when it's in one position, A, we want damper A, which is indicated here, open, and damper B closed. And then when I change that selector switch to B, we want the reverse to happen. So then we want sort of A to close and B to open. And to achieve that, that's kind of how we're doing the control through this relay here.
Okay, that's fine. So then just looking at that, how, in terms of the control we've got there, how much of that is our design, as it were, and how much of that is how the terminals are presented on the damper?
Yeah.
Yeah.
Good question, man. So these linear dampers like are very basic, very straightforward. And I'm going to show you on the next bit, mate. We're going to look at a more in-depth damper actuator, which I think is going to be more what you're interested in. It's with these ones, it's literally 2 cables. You've got a positive cable, you've got a negative cable coming out of the damper. So yeah, you've basically, you can't quite see it, but there'd be like another, this is like the actuator motor, and then you'd have another cable coming out, and it's literally, it's just got a positive and a negative, as you can see here, positive and a negative, and that's it. You basically power it to open, or you power it to close. You sort of just switch the polarity. Very basic, mate, on those ones. We're going to get to the more complex Belimo actuator control in a second, mate.
Sure.
Also, Marlon, because I think you missed what I mentioned at the start. If you go into Squad and you go to classrooms, training courses, and then go down to this one, how to pre-commission a control system, and go through these lessons, there's like 12 lessons. Mm-hmm. This will show you the project. And so this is like the schematic and the actual panel that I'm testing that you're seeing here in these here, and you'll actually see me testing it, so you'll be able to visualize what I'm talking about better.
All right, quality, excellent.
Before we move on to the more detailed actuator, guys, does anyone have any more questions around this and what's happening here?
So, Chris, this damper is literally just fully open, fully closed. That's it.
Yeah. Now you can say what we could do is we could, if we were using it in a different application, we could say it takes 10 seconds to go from fully closed to fully open. We could just apply some power for like 5 seconds if we wanted it to move to 50%,
right,
and then just cut the power. Yep. So there, with these dampers, there is some level of control and modulation, but in terms of this project, how we're using it is it's just fully open, fully closed.
Okay, thanks.
Cool. All right, guys, I'll move on to the next phase. So that was a vertical damper. Now, these Belimo actuators are probably far more common, and you'll see them quite a lot in industrial projects, and a lot in BMS projects as well. And in a lot of plant rooms, you'll see these Belimo actuators. So let me show you. So what I'll do, guys, I'll just drop this in the chat. And what I'll do, I'll put all of these resources in the squad. So, if you want to come back to all these resources later, you can. But this is the example actuator that we're looking at. And this is a really good website, guys, for any control hardware, certainly for building management or anything to do with control panels. EC Products, if you're based in the UK, is brilliant. Really, really good website. It's got everything you need. Yeah. So this is what we're looking at now. And this is the tech manual. Again, you can get that tech manual off this EC Products, but this is what it is. And these Belimo actuators, or any type of actuator really, doesn't matter if it's Belimo or not. Like you can usually get different control voltages. It might be 24 volts, it might be 230 volts, AC. They come in all shapes and sizes. This one that we're looking at, not that it really matters because we're looking at the control and the wiring of it, but just so you know, this is like an AC or DC voltage. So we can use 24 volts AC or DC to control this actuator. Just to recap as well, guys, so you can visualize. So this is another picture of what it looks like, a slightly better picture. What this does, this fixes to a chassis of a vent, basically. So as you can see here, it kind of just fixes to this chassis, and then it connects to a shaft that you can see here, and then that actuator kind of rotates one way and rotates the other way, and then as a result it turns that shaft, and that shaft is connected to these vents. So similar to that vertical damper, the linear damper, we're kind of we're doing the same thing, but like in a different orientation, different style, like using sort of slats, as you can see here. So we're opening the slats or we're closing the slats. So that's what it looks like in situ on a ventilation system. So going back to the data sheet. Let me just check. We're on track. Tech manual, image. Yeah, cool. So I'm hoping at least, Marlon, that this was what you were more kind of getting at in terms of like actuator control and the wiring and whatnot.
Yeah. To be fair, this is sort of pretty much exactly the kind of thing I had in mind, to be fair.
Great, cool. So we're looking at now like the wiring diagrams, as you can see here from within the tech manual. So I'll say it every time, guys. RTFM, read the fucking manual, because then you'll understand, or you'll have a much better understanding of how that piece of equipment should be wired, how it works. Rather than sort of leaving it up to sort of guessing, it will give you like most of what you need. You might still need to get a full understanding, like actually test it and potentially power it up and test it on site, but this will get you much closer just having a read through this. So I'll encourage you to RTFM. So as you can see here, we've got like two cables coming in. So one of those cables, and we can use this actuator in two different ways. So let's just initially look at it in terms of just open and closed. So similar to how we were controlling those previous dampers, where they were just opened or closed, that's what we're going to look at first with this rotation damper. So actually, the first thing that we'll look at is just the easiest thing to look at, and it's the same on both control methods, and that is S1, S2, and S3. And we've got an indication here of what that's actually doing. So we got like 0% to 100%. So who can tell me like what is going on here without looking any further into the tech manual? Does anyone know what these are being used for? S1, S2, S3?
They just look like digital inputs. So S1 might be, I don't know, 0, and then you've got S3 for fully open, and S2 might be for in the middle. But I think they look like digital inputs to me.
Not quite, mate. Does anyone else have any idea of what these are? Okay. So if we look a little bit further down here, yeah, I think that's it. We've got, it basically tells us here, auxiliary switches. So what are auxiliary switches, guys? Can anyone tell me? What might be more familiar to some of you is like if we look at let's just take a basic heating or hot water system in our homes, and we've got a valve, right? We send be difficult for me to explain this without like drawing it. I don't want to confuse things, but basically those valves, we send power to those valves, and when they get to when they fully open, like we send say 230 volts to this valve in our hot water system. Once that valve like fully opens, our auxiliary switch on that valve will then close, which then means that we can send that signal, the signal that tells us that that valve is fully open. We can then use that signal to then trigger the pump in our hot water system.
Is it like a PID system? Sorry, Chris.
What's that, mate?
Is it like a PID system?
No.
Okay.
So I'd say no because I don't want to confuse things. PID is more sort of like modular, using analog signals, and we're controlling things open and closed dynamically in real time. But let's not get into that on this session. What an auxiliary contact is it's basically it's a switch. So Marlon, it's actually an output. So let me explain what this is doing on this valve, or sorry, this actuator, because ultimately a valve.
Sorry, Chris. Just looking at the example you've given, I don't know, I'm not correct. I think it makes sense. So with a standard heating system, we'll send a signal out typically to our 2-point valve actuator. That will rotate around, and that then brings into play that basically connects to. So it's like a sort of it's like a switch that tells us what a given situation is.
Yeah.
Right, so when that contact closes, we know there's a call for heat, and that switch essentially tells us, yes, we have that call for heat. That then sends an output, as it were, to the heat source, for example, to that sort of thing. Am I thinking along the right lines? Okay.
That's it, mate. Yeah. So it's basically, it tells us the state of something. So just going back to the hot water system, like it tells us, like when we send power to that valve to open, and then when that valve is fully open, the auxiliary contact then sends us or can send a signal to something else to tell us the status of that valve is fully open, which we can then use to like bring on the pump, because we don't want the pump to come on before the valve is fully open. We don't want a pump to burn out running against, a valve that's closed. So in a similar way, what we're doing with these contacts here, S1, S2, S3, is, and you can see here, we've got 0, 100%. So what do you think S1 is doing? Let's forget S2 at the moment, but what do you think S1 is doing here? And what do you think S3 is doing here?
One is communicating there's no demand, and the other says, "Oh, I'm fully open. I'm at sort of full capacity."
Yeah. So just change your wording slightly, mate, just so it's more just to clarify for people. It's not necessarily demand, because the demand comes from elsewhere. But you're right in what you say. This S3, if we connect a cable into S3, when this actuator is fully open, 100%, that switch will switch, and then we can send a signal out on S3, and we can do whatever we need to do in the rest of the system to tell us that vent that we're looking at in this situation is fully open.
Mm.
And we can also do exactly the same thing. We can send a signal out on S1 when that vent is fully closed. So if we're thinking in terms of a BMS system, we can monitor, we could like just think of it in simple terms, like we could have like 2 lights on the front of the panel, one that says open, one that says closed. So S3 would go back to our green light, let's say, on the front of the panel that indicates this ventilation duct is fully open. And then S1 would be wired back to the the red light that says that damper is fully closed. That not that we'd necessarily be doing that in a real BMS system, but that just gives you a taste of kind of what we're doing there with these control signals.
And then with that, Chris, you could take that back to a 2-pole relay, couldn't you, to get both your panel lights activated and also back to your sort of PLC.
Yeah. Which then we're going a step further now, is like, you might want to do this, you might want to use these for like just external monitoring. So we can log into the system remotely as BMS engineers, and like if the operator on site or whoever the engineer on site is, maybe it's a heating engineer or ventilation engineer, we can kind of see the state of this vent remotely just from having these 2 S1 and S3 wired into our BMS and then into our PLC. And we can then control this remotely and see that these statuses are changing. Because if you think about it, let's say there is a problem on this vent, and we're checking things remotely. So we're sending a command to open this vent, and so we're switching it on to fully open, but then we're not seeing a signal coming back on S3 to tell us that the vent's fully open. So that would then lead me to think there's like some sort of, well, it could be multiple issues, but what's certainly happening is that this vent isn't opening. There's an issue there, whether it's like a problem with the cabling, maybe a cable's been cut, maybe it's a mechanical issue with this vent, maybe it's jammed up and some bearings have, come loose or worn out or whatever. It could be anything, but that just verifies to me off site that, yeah, well, that's where the problem is. That vent isn't opening. And that helps us focus where the problem is, So it's kind of it helps us do fault finding and just like status and monitoring and whatnot. I've just fucking realised that I've got a call in 15 minutes. So yeah, Thomas, mate, we might have to come back and do your question another time, mate.
Yeah,
Next
it's
week.
fine. That's fine.
Sorry, bud. I didn't realise this. I didn't think this would go on so long. But we'll definitely cover your question on the next session, or I'll do like an offline Loom one for you.
Yeah, okay, cool. Whatever is easier for you.
Okay. Yeah, so that's that basically. These are our auxiliary switches. So S1 switch, and a switch kind of indicates that it's an output. It's like we're sending a signal out. That's probably not a good way to think about it, actually. Ignore what I just said there. But yeah, that's what they're doing. It's telling us the status of this damper. Is it fully open like it is in this position here? If that was the case, we'd have a signal going out on S1. And then when it's fully closed, we'd no longer have a signal going out on S1. We'd have a signal going out on S3. Or sorry, that might be the other way around, but you get one. You get my point. So that's exactly the same thing for both ways of controlling that damper. Like as you can see, S1, S2, S3, it's the same. There are auxiliary switches telling us the status of the vent. Now, in terms of the control, if we're just using open and closed, so the wiring, and let's just go back to a picture quickly. So we've just looked at the wiring and the cable on this side of the actuator over here. Now let's look at the wiring over on this one. So what it is we've got our 0 volts. So 0 volts, that just goes in on 1. And then we've got, it can be AC or DC, but 24 volts. So then we've got 24 volts, a constant 24 volts that's going in on 2. So what would be happening now? Let's think about it in terms of the operation. So what would be happening now? We got that 24 volts on 2. That would then be closed. We're powering that closed. So it's closed at the moment. And now we've got a little switch here. So this might just be like a relay on a PLC or something, or it could even just be like a switch on the front of a panel. Doesn't really matter. We just, as you can see, we're just closing a circuit here. So currently we've got power going into 2. That's closing the damper. Then if we close this switch here and also apply 24 volts to terminal 3, now what's going to happen is we've gone from closed, now we're going to go open. So that's going to, as long as we've got that 24 volt applied on 3 now, that's going to open. As soon as we remove that power on 3 and we open this circuit again, whether that's a relay on a PLC or a switch on the front of the panel, as soon as we remove that damper's going to close again. Make sense?
So that relay then will get a signal perhaps from our PLC, for example. So you may have an input device, goes back to the PLC, says, okay, we need some fresh air. That will then send the signal out to this particular relay to force it closed.
Yeah.
That kind of process.
Yeah, that's it. Yeah. This might, so that example that I just gave, where it's kind of normally closed, where we're applying the power to the number 2 constantly, which is closed. It might be, and I don't know this for sure. You don't really know until you test the operation. It might be, and you might actually be able to adjust this through these switches, little dip switch things and rotary switches on the front of the actuator. But it might be that if we're powering it constantly, it might power it open. And then when we close that relay over here, it might close it. It will just, depend on the application whether you want it sort of like if that relay on the PLC, like if the PLC fails, we might want it to fail safe closed, or we might want it to fail safe open. So you need that comes into sort of the operation here. It's not that important, but it's just something to be aware of. I'm going to move on to this 3-point control, and then hopefully I'll cover that in 5 minutes, and then we've got 5 minutes at the end to cover questions. So this now, let's just think of this as the easiest way to think about this would be like a 3-position switch. So like a 3-position cam switch on the front of a control panel. Now, you'd most likely be doing this control through a PLC as well, but just for simplicity's sake and to visualize what we're talking about here, let's use a 3-position cam switch. And switch. Basically something like that. Let's just imagine it's something like this doing the control at the moment, okay? So when it's selected straight up 0, like it is in this picture here, that arm here is just connected to 0, so nothing's happening. Like that vent is just wherever it is, you know, whether it's been left fully open, fully closed, or 50% open, 20% open, 20% closed, whatever. It's just wherever it is. Where are we at? Now, let's say that we switch this cam switch to ignore like the hand and the auto labeling. That's irrelevant. That doesn't matter. Let's just ignore that. But let's say we switch this position to hand, and hand is correlated to 2. So we switch that to 2, and now that is, let's say it's opening. And let's say that it takes like 10 seconds for simplicity's sake to go from fully closed to fully open. So if we apply that power for 10 seconds to number 2, that will now go fully open. Then if we then switch that switch over to auto, which is 3, and we apply that for then 10 seconds over this way, that will then close it. And then if we bring it back the other way, back to 2, and we power it for 5 seconds, then that will open that vent to 50%. So on this 3-point control, it's kind of, we've got, it's not fully open or fully closed. We can basically modularly control it by applying power for X amount of time to open it to a certain percentage or close it to a certain percentage. Does that make sense, guys?
Yeah.
Hello, Chris. Yeah, that makes sense. I do wonder though, with things like this, would you not more likely use, I mean, you can tell me, a sort of 1 to 10 volt type setup to indicate to what extent you want it open, like 2 for 20%, 3 for 30%, and so on and so forth? Because that must be quite, this method is fine, but it does seem a little bit, this seems a lot trickier than, you know, having a sort of 1 to 10 volt system, which indicates exactly how much you should be open or closed.
Yeah, you could do exactly the same thing using a 0 to 10 volt analog control signal. Like the same operation would apply. So you apply, I don't know, let's say 0 volts, it would be fully closed. 10 volts, it would move to being fully open. 5 volts, it would be 50%. So yeah, you can there's actuators out there, Belimo actuators, that where you can use an analog signal for the control.
Okay.
Yeah. Like there's so many different like power voltage, like power supplies, different power supply voltages, and then different control methods as well. This is just using digital signals to control it. But of course, we could do exactly the same thing using a 0 to 10 volt control signal, or a 4 to 20 milliamp control signal, or a 0 to 20 milliamp control signal. But ultimately, we're in terms of the mechanical operation, it's the same thing. It's the same outcome.
Okay. All right, great. So that's just a matter of valve selection then, depending on you sort of, I suppose you'd look at your preferred control strategy and then say, right, that's a particular actuator we need to get to fulfill the role in this fashion.
Yeah, and it might be that, price might come into it. So if you're, generally speaking, analog control methods are usually more expensive. So like the modules, like an analog control module is more expensive than a digital like module where there's just relays. I think there might even be like a difference in the price of the actual actuator as well. I think they're generally more expensive if they're analog. Don't hold me to that, but you see what I mean. So like there's variables that come into it, whether it's digital control or analog control.
And just so you know, we help engineers, electricians and technicians land new careers within the controls, automation and BMS industry in 12 weeks. And we also help business owners add an additional 100K in revenue by bringing all controls, automation, BMS in-house. So if that's you, we might be able to help. There's a link in the description.